Okay, so let's continue. So last time we derived the Heisenberg equation motion for two very simple operators A. One is when A is x position operator, and another is when A is a momentum operator. And then we write down and derive this Heisenberg equation motion for x and for p, and we derive this quantum version of Newtonian equation motion like this. So this is the quantum version of the equation motion for an object. And this looks very similar to Newton's equation motion because the term on the left-hand side of the equation is the mass of the particle times acceleration, m times a. And on the right-hand side of the equation, this looks like the derivative of the potential with a minus sign, which is precisely the force in Newton's equation motion, right? However, there's a troublemaker, and this troublemaker is this expression value right here. So we want to actually make a link between this quantum version of equation motion and the classical Newtonian equation motion. So in Newton's equation motion, this is what we're familiar with, right? There's no bracket, no expression value, nothing. It's simply just a classical vector and the second time derivative of the x classical times the mass is equal to the force. And the force is given by the gradient of the potential, classical potential, and the derivative of v classical with respect to this x classical. X classical is just some position vector. So they have more or less the same form except this expression value right here. So the question we want to address is, under what conditions are they really equivalent? Okay? So if I simply just identified expression value of the x operator as x classical, but then we should also identify this dv dx with the expression value as the v classical, the x classical. So we need to really make such a identification, right? So they are equivalent only if both are correct. Okay. So, but the first line is all right because this is what we could imagine, that this classical vector, in some sense, is just the average or expression value of some x operator. However, the second line right here should put a question mark. And the reason why this is questionable is because this is not always true, not always correct. Remember, this where you put this bracket or expression value matters. Okay, so this on the left-hand side of this equation, you get dv dx and everything with expression value, but on the right-hand side, this expression value only applies to the x operator, right? So as a result, you will see that dv dx, everything, taking the expectation value of the everything, is not the same as dv dx average. The reason is the following. Okay, so the force is given by minus gradient of v with respect to the position. However, this force is a function of the position vector x, but you can actually separate this x in terms of this x average plus the fluctuations of x away from this average value. So you can consider this expression value of the x operator as some kind of a average of this position vector. Okay, and of course this and any arbitrary position x, f of x, could be expanded in terms of the f of average x plus the Taylor expanded terms. At first order, this is just the first derivative of force with respect to this x and taking this x to be an average value, and times this small deviations right, between this x position and x average, right, plus the higher order term. And remember, the right-hand side of this equation or inequality right here says that this dv as a function of x average by dx average. Okay, so what is this? This is nothing but the first term. This is just the first term. This is just the first term. Okay, and if we really want to do the Taylor expansion around this x average, we need to also consider the other term, okay, the higher order term in Taylor expansion. So there is additional term like f prime times the deviation delta x and so on and so forth. Okay, so if I take this expression value of this on both sides of the equation, I get f of x average, which is everything average f of x average plus f prime delta x average plus higher order term average. Okay, so the left hand side of the equation right here is precisely this one with a minus sign, right? Okay, so in other words, the left hand side of the equation, this left hand side of the equation in the bottom line right here, so this is not the same as just the first term of the Taylor expansion. There are additional terms which we should not ignore. However, under one condition can we ignore such a high order terms, and this condition is that when this delta x, if delta x or delta x squared is actually the standard deviation, right? The square of the standard deviation square is really, really small. It's really, really small. So if the standard deviation of this position vector and the average of this position vector is really, really small, and I can neglect this term. So all the rest of this correction beyond this zeroth order approximation can be ignored only if the standard deviation is really, really tiny. So in other words, if the standard deviation is really, really tiny, then these two quantities are approximately the same, only approximately the same. Okay, and as a result, the quantum to classical equation motion shows very similar mathematical form. However, depending on whether the standard deviation, okay, so if the standard deviation is really, really small, and we could consider the quantum Heisenberg equation motion approximately given by Newton's equation motion. However, if the standard deviation is not small and it cannot be ignored, then this quantum version of equation motion is not identical to the classical Newton's equation motion. You get that? Okay. So therefore, the condition under which the quantum and classical equation motion approximately correspond to each other is this condition right here. If the standard deviation, which is the width of the broadening of this wave function that we introduced earlier, remember that, right? So this is the width of your distribution in wave function. So if this width is really, really narrow, you get a very sharp distribution of your wave function. In that case, and quantum classical equation motion are approximately the same. But if not, then they are not the same. Okay, good. So I guess that's for chapter 5. So let's take a short break. When we come back, we continue with chapter 6, which is the operator methods in quantum mechanics. Okay, so far so good. 这接下来的部分就是真正进入到量子力学的核心的部分也就是用矩阵跟狄拉克的算符来重新的来理解那个 Schrödinger equation 跟量子力学的运算。Okay, so let's turn to a new chapter, which is the Dirac notation in quantum mechanics, which is somewhat new to most of you. Okay, so but it's not totally new because we already introduced this concept of this matrices, okay, matrix product and matrix representation of a Schrödinger wave function. So as we already identified previously, that the wave function psi, or this conjugate wave function psi star, shows the analogous expression in vector space, right? In Hilbert space, I mean. So this psi of x could be considered as a column matrix like this, with the matrix element psi 1 up to psi n, where psi 1 up to psi n are the value of this wave function at particular discrete position x1 and xn. And you mesh all this position space in infinite number of points, and you attach this value of this wave function to the matrix element in the corresponding component, like this. Okay, so this is what we defined earlier, that you can mesh this position vector or position space in infinite number of points, and then you could discretize all this Schrödinger wave function in terms of infinite number of values, okay, or matrix elements right here, and you call this column matrix for psi, and you call this row matrix for psi star. So here, Dirac, which is a very smart theoretical physicist who invented this notation called the bracket notation for this column row matrix. And we know that the bracket is nothing but this symbol, which is made of two kind of symbol like this. You actually want to include something, and so you put a bracket on both sides of that something that you want to emphasize. And so he defined that this column matrix is so-called a cat-state, and the row matrix is what he called the bra-state. Okay, so the word bracket consists of two parts. The left part of the bracket is bra, and the right part of the bracket is cat. Okay, so and that's how you define this row and column matrix like this. So if you make an inner product between the bra and the cat state, you really form the bracket, right? The bra is on the left, where you have this kind of angular stuff on the left part, while this cat state, you get vertical line on the left, but this kind of a bracket notation on the right. So if you enclose this bra and cat state in the inner product, and you really form the bracket. Okay, so Dirac used this shorthand notation to represent such a column row matrix that we discretize from the Schrödinger wave function. So we could rewrite everything Schrödinger wave function and this Schrödinger equation and all this quantum mechanical operations in terms of the Dirac notation, namely Dirac bra-state and cat state and their overlap or inner product. So let's just define this inner product or the orthogonal nature of this wave function. Suppose we have this two eigenfunctions, which are labeled by um and un. And previously, without this Dirac notation, this is simply just the overlap integral that we defined earlier, right? So this is the overlap between these two wave functions, and these two wave functions happen to be eigenfunctions of some quantum mechanical problem, um and un. So the result is Kronecker delta function, delta mn, where this is 1 if m is the same as n, and 0 if they are not the same. Okay, so this is well known. But now Dirac invented a much simpler notation, since you know that this um start is nothing but the bra-state, where you have this kind of a notation, and you have this, there's the left part of the expression value. That's simple. appearing on the left, but its cat state, you have this half of the expression value symbol on the right. Okay, so, and you could discretize this position vector x just like what I did, and you convert this integration into a summation. Okay, you sum over all this matrix element xn or xi. Okay, and this is what? This is psi of u m of xi un of xi. Okay, so this is the i's component of the row matrix on the left. On the right, this is i's component of the column matrix right there. Okay, m and n are the labels of their eigenstate. Okay, so, and you sum over all this discrete points xi. And I can define this as a very simple notation, which is nothing but the bracket notation, right? Right here. So I define such a complicated integral, and I use Dirac bracket notation, and this is nothing but the inner product between the Dirac broad state and the Dirac cat state. And this is the inner product of the broad and cat. Okay? So isn't that simple? Isn't that wonderful? Great. And you could generalize this idea to consider the inner product between any two different arbitrary wave functions. You could generalize this. You could consider the overlap integral between, say, phi and psi. And you can define this by using Dirac bracket notation. It's just this. Okay, so inner product between this state phi and state psi. So in other words, the inner product between phi and psi is the same as the overlap integral between phi and psi. So this is what we are familiar with in the previous chapters, and this is the same thing that we defined earlier, but with Dirac notation. So you may wonder, why bother, since we are saying the same thing, right? So we are describing the same equation, so why bother? Well, you will see the reason why it's a great advantage to define Dirac notation and use this notation for further calculation, because it's greatly simplified, and also conceptually it is really useful. So we simply just detach the Schrödinger wave functions from the more abstract quantum state. So, but we will come back to this later. So let's just finish the definition, right? So if you consider the star of this overlap, you simply just interchange, switch the order of the Dirac broad cat state. So remember, when you take the Hermitian conjugate of this column matrix, you get a row matrix with the start in the matrix element and vice versa. So the column matrix becomes the row matrix, the row becomes the column, and also subject to the complex conjugation. So you can see very clearly, you simply just interchange the order between phi and psi and put a star. So double star is no star. Okay, so this is precisely the star of the overlap integral. And you could also take advantage of this linearity of this wave function and their linear combination. And it is simply just follow the linear algebra. Okay, so and everything's the same, except now we adapt the Dirac smart notation, right? We do nothing. We simply just rewrite everything in terms of Dirac notation. That's it. There's nothing new. But there will be something new in just a moment. So you may just consider the operation of a quantum state by operator A in Dirac notation, right? So remember, as we defined earlier, that the quantum mechanical operation is nothing but the matrix product, right? So any quantum mechanical operator could be represented by n by n matrix, right? So n by n. So, but this Dirac cascade psi is a n by 1 column matrix, right? So the product of n by n by n by 1 reports to you an n by 1 column matrix, which is again some quantum mechanical state, which is different from psi, because when you make such a matrix product, it is guaranteed that you'll get a different column matrix. So phi in general is not the same as psi, but still is a quantum mechanical state. And we can call this A acting on psi as another quantum state. Because as I mentioned, so if you translate this state, I will say that this operator A, when acting on psi, will give you another Dirac cascade, which I call this phi. So state phi is some quantum state. Okay, since it is some quantum state, of course, we could just write it inside this Dirac bracket notation, right? Okay, so in other words, it's more convenient for you to actually rearrange this operator and quantum state inside and outside of Dirac notation if I simply adopt this Dirac notation. Okay, so which means that the operator, when acting on a cat state, we get another cat state. Okay, so likewise we could rewrite the definition that we defined earlier regarding activation value of the A and A dagger, but in this Dirac notation. So the general inner product, this is a more general inner product, could be constructed between any Dirac broad state phi and another Dirac cascade, which I call this psi theta. Well, this psi theta is made of an operation of an operator, a Dirac cascade. Remember, the operator acting on the cascade is another cascade. Since this is another cascade, which I call psi theta, and then I can simply just replace psi theta by this quantum mechanical operation, which is A acting on psi. All right? So therefore, you can consider any quantum mechanical inner product like this as like this operation really happened like this on the left-hand side. So likewise, you could consider even more general inner product in Dirac notation. It's like use this operator B, you actually apply to some quantum mechanical broad state phi, and you make inner product between this state, the broad state, and the cat state, which is the result coming from this A operator acting on psi. Right? So this is inner product between phi theta and psi theta. Yes? In other words, any Dirac broad cascade could be considered as the operation of any operator A or B acting on some cascade or broad state. So this concept is really, really useful, which we emphasize many, many times. An operator acting on some Dirac state or some quantum states is another quantum state. Great, so we can take advantage of such Dirac notation, and we can rewrite this definition for a dagger, the Hermitian conjugate of the operator A. Remember that we define this A dagger through this kind of overlap integral, right? So that's what we defined as A dagger previously in chapter 5. So a dagger is defined through this kind of overlap integral, which is overlap between some wave function, which I call this phi theta, which is made of this A operator acting on this phi. And I take the start and make a product between phi theta star and psi. And by earlier definition of a dagger, this is the same as I switch the order between A and phi and I put a Hermitian conjugate on both objects. I get phi star on the left and a dagger on the right. And so this a dagger appears right here following this way of defining this Hermitian conjugate of the operator. But here I could use a Dirac notation to further simplify this a bit of lengthy expression in the integral like this. So I could simply just rewrite this in terms of Dirac-Brown-Cat state. This is nothing but the inner product between a Dirac-Brown state, which is made of A acting on this Dirac-Brown state phi, and Dirac-Cat state psi, right? So this is, you could simply just translate this overlap integral in terms of this Dirac-Brown-Cat state notation. So, and as I mentioned, you could simply just define this a dagger by switching the order of A and phi when you really move this operator A to the middle of this inner product. So this is precisely this complex conjugate of this inner product. Imagine that this phi is just A times phi, right? So this is precisely another definition of a dagger through Dirac-Brown-Cat notation. And you could simply just identify these two expressions to be the same. So this is the same as this one. And indeed, they are identical, because if you simply just translate this Dirac notation back to the overlap integral, this is precisely what you should get. But the advantage of using this Dirac notation is that you don't bother writing down all this complicated integral, and this is much simpler because you have only this Dirac and Brown-Cat states. That's all. No integral, no complicated this equations, and this is the much elegant way, much more elegant way. So let's just summarize. Following this Dirac notation of A and A dagger within this inner product, and you get this identity. So if I take the start of this A phi in the product with psi, I get this interchange of phi and psi on both sides. Because if you take a star of this A dagger in between this Dirac-Brown-Cat state, and you should remember you put the dagger on the A dagger. So A double dagger is no dagger. Up to now, there's no new physics except that we simply just adapted the Dirac notation to simplify all this lengthy calculation regarding the Schrödinger wave function and all these quantum mechanical operations. So let's take a short break. When we come back, we will again rewrite this Fourier expansion theorem and via this Dirac notation. Okay, so the goal of this course is to cover at least to chapter 8 or 9, and I'm hoping that we could cover partially the spin angular momentum. Okay, 这部分就是量子力学的核心的部分哈，就是需要用狄拉克的符号，然后重新来理解量子力学的这些运算以及薛定谔方程式等等。那我们之后会来说明为什么狄拉克的符号是有用的除了它简化计算之外，另外最有用的部分就是它能够让我们可以区分什么是这个 arbitrary 的 quantum state， 以及就是说什么是量子状态量子态 quantum state 跟这个波函数之间的关系我们到目前为止都 把这两个概念就是当作是同一件事情，就是量子的状态就是用薛定谔 wave function 来描述哈。但是呢，我们一旦用了狄拉克的符号之后，这两件事情就未必是一样了哈，就未必是。其中 quantum state 的这个位阶是更高的哈，它是更抽象的概念。那薛定谔 wave function 只不过是把这个量子状态把它投影到我们的时空间哈 real space。那这两个概念是完全不一样的层次的概念哈，我们之后会提到。So let's just look at this expansion theorem. I can simply just safely replace all this Schrödinger wave function psi of x in terms of the Dirac cat state, right? So which I defined already. So phi is the Dirac cat state can be expanded in terms of a complete set of eigenbases. Remember that, which is made of all these eigenfunctions. Remember that. We once used this phi n of x, right? But here, I can simply just adapt the Dirac notation since this phi of x, phi n of x is nothing but some wave function. So I can rewrite this in terms of Dirac cat state, which is made of all this column matrix element. As a result, I can simply just use this Dirac cat notation. And this coefficient Cn is nothing but the overlap integral between this eigen state and the arbitrary function, arbitrary, Dirac cat state psi, right? Good. Time is up, so let's stop here. So on Wednesday, we continue describing the consequence of this Dirac notation and the power of Dirac notation. See you on Wednesday.